March 23, 1881. Cass, West Virginia. The coupling failure that would rewrite every assumption about locomotive power was about to reveal itself on a mountainside so steep that railroad engineers had declared it impossible to log. Ephraim Shay stood beside his strange-looking locomotive as it strained against 47 tons of virgin timber on a 14% grade that conventional engines couldn't even attempt. Steam hissed from cylinders mounted along the side of the boiler, driving a system of gears and shafts that every railroad expert in Pennsylvania had called mechanically unsound. The locomotive's wheels turned slowly, methodically, gripping rails that were barely more than logs laid in the mud. Then the sound every engineer dreaded, the sharp crack of an overstressed coupling. But instead of the locomotive rolling backward down the mountain, Shay's machine held position. The vertical cylinders continued their rhythmic pulse. The gearing system absorbed the shock load that would have destroyed a conventional locomotive's drive wheels. Within 40 seconds, the train was moving forward again, dragging its massive load upgrades that standard locomotives couldn't climb empty. Eastern railroad authorities had been right all along, everyone believed. Small locomotives with complex gearing couldn't compete with the proven power of traditional drive wheel designs perfected through 50 years of American railroading. The engineering consultants from Baltimore and Ohio had been explicit. Vertical cylinders and gear drives represented theoretical possibilities, but practical impossibilities. Too many moving parts, too much friction loss, too much at stake to trust logging operations to machinery that violated every principle of efficient locomotive design. But in that moment of mechanical crisis, as Shay watched his odd little engine do what larger locomotives could never attempt, he understood something the railroad establishment had never considered. The problem wasn't that small engines couldn't move heavy loads. The problem was that railroad engineers were building locomotives for smooth, level track when they should have been building them for the brutal reality of mountain logging. The morning fog clung to the Appalachian Ridgeline in 1878 as Shay walked through yet another abandoned logging camp in Michigan's Upper Peninsula. The sound that defined these failed operations was always the same. Silence. No steam whistles, no saw blades, no teamsters shouting at ox teams struggling to move timber down, grades too steep for conventional transportation. The economics of the lumber industry in 1878 were brutally simple, but maddeningly inefficient. Michigan held 150 billion board feet of standing timber worth $2.3 billion, but 60% of that forest was on terrain too steep and remote for ox teams to reach profitably. The mathematics of muscle-powered logging limited harvest operations to grades under 8% and distances less than 4 miles from sawmills or river transportation. Shay examined the rotting skid roads where logging companies had tried to drag timber using teams of 16 oxen. The deep gouges in the hillside showed where multiple attempts had failed, where animals had been injured, where loads had broken loose and crashed back down the mountain. At 37 cents per 1,000 board feet for ox team hauling, timber operations could barely break even on accessible terrain. On steep mountain slopes, muscle-powered logging was simply impossible at any price. The obvious answer was locomotives. Machines that could theoretically move far more weight than animals, but conventional railroad locomotives of the 1870s were designed for one specific environment: smooth, level, carefully graded permanent track with curves no sharper than 12 degrees and grades rarely exceeding 2%. Logging railroads needed to operate on temporary tracks laid directly on forest floors, following terrain that included 14% grades, 40-degree curves, and rails that shifted daily as the ground settled. Standard locomotives with their rigid wheelbases and smooth drive wheels simply couldn't function in these conditions. Shay visited a failing logging operation near Cadillac, Michigan, where owner Nelson Brown had tried using a conventional 12-ton Porter locomotive on a logging track. The machine sat silent beside a twisted section of rail, its driving wheels polished smooth from spinning helplessly on grades that barely reached 6%. Brown's financial records told the story clearly. The locomotive had operated 23 days before suffering frame damage from track irregularities. Repair costs had exceeded $340, and the machine now sat unused while ox teams struggled to move timber at rates that guaranteed financial losses. "Mr. Shay," Brown explained, walking around the damaged locomotive, "the problem isn't power. This engine has enough steam pressure to move twice the load we're attempting. The problem is that railroad locomotives are built for railroads, not for logging. Brown pointed to the locomotive's drive wheels, which were 42 inches in diameter and perfectly smooth. On a proper track, these wheels grip through weight and friction, but on muddy, uneven logging tracks with grades this steep, they just spin. We can't carry enough locomotive weight to maintain traction without breaking through the temporary track structure. Shay had been studying this exact problem for 6 months, and he understood that Brown was describing only part of the challenge. Conventional locomotives also suffered from rigid wheelbases that couldn't negotiate the sharp curves and uneven track that logging operations required. A standard locomotive's fixed wheelbase of 8 to 12 feet meant that curves sharper than 12 degrees would cause wheels to bind or derail. The engineering establishment had a clear explanation for why locomotives couldn't work in logging operations. Professor James Blackwell, whose textbook on locomotive design was required reading at every engineering school in the Northeast, summarized the professional consensus in his 1877 analysis. Locomotives require consistent track geometry, adequate rail weight, and properly graded roadbeds to function efficiently. Attempting to operate steam locomotives on temporary logging tracks violates fundamental principles of railroad engineering and will inevitably result in mechanical failure and economic loss. The lumber industry trade journals echoed this assessment. Northern Logger magazine published multiple articles explaining why logging would always depend on animal power for difficult terrain. The mechanical limitations were simply insurmountable. Locomotives needed conditions that logging operations could never provide. But Shay saw the problem from a different perspective. Railroad engineers had spent 50 years optimizing locomotives for railroad conditions. They had created magnificent machines that could pull 300-ton trains at 45 miles per hour on a properly maintained track. But they had seriously considered building a locomotive specifically designed for the opposite conditions: slow speeds, extreme grades, sharp curves, and temporary track that shifted constantly. What if a locomotive didn't need smooth drive wheels and rigid frames? What if it could grip track through gearing instead of friction and follow curves through a flexible drive system instead of a fixed wheelbase? The disaster that taught Shay everything about gear-driven locomotives began at 9:15 on a Saturday morning in June of 1880. His first prototype sat motionless on a test grade outside his sawmill in Herring, Michigan, surrounded by shattered gearing and a drive shaft twisted into a shape that looked like a corkscrew. The failure had been spectacular and expensive. The locomotive had successfully pulled 8 tons of logs up a 12% grade before the entire drive system had come apart under load. Gears had stripped their teeth. The vertical cylinders had continued running, but with no connection to the wheels, the locomotive had simply stopped moving. The crash of breaking metal had been loud enough to bring workers running from the sawmill a quarter-mile away. Shay crouched beside the wreckage and began his analysis. The drive shaft, which connected the vertical cylinders to the gearing system, had failed at its weakest point, where it turned 90 degrees to engage with the truck-mounted gears. The metal showed clear signs of torsional stress, the twisted grain pattern that indicated forces exceeding the shaft's structural capacity. Back in his machine shop 2 weeks later, Shay spread out the failed components on his workbench. Each piece represented a specific engineering lesson. The stripped gears showed that his original tooth design had been too shallow, unable to handle the shock loads that occurred when the locomotive encountered track irregularities. The twisted drive shaft revealed that his 90-degree power transmission angle had created stress concentrations that normal operation would inevitably exceed. But the most important lesson came from what hadn't failed. The vertical cylinders had continued operating perfectly throughout the disaster. The truck-mounted wheel assembly had remained intact. The fundamental concept, using gears to transmit power to all wheels simultaneously, was mechanically sound. The problem was that Shay had been building his gear system like a factory power transmission when he should have been building it like a battleship drivetrain. Shay began calculating the actual forces his locomotive would encounter. On a 14% grade pulling 40 tons, the drive shaft would experience peak torque, loads of 14,700 foot-pounds, 3 times what his original design could handle. The gears would see shock loads whenever the locomotive hit track irregularities, requiring tooth profiles strong enough to absorb impacts without stripping. The engineering challenge was distributing power to all wheels while handling variable loads, absorbing shocks, and maintaining operation even when individual components were stressed beyond normal limits. Shay's original design had treated the drive system as a simple power transmission. His redesign would treat it as a critical structural component that had to survive conditions that would destroy conventional locomotive machinery. Material selection became crucial. His original gears had been cast iron, adequate for factory applications but too brittle for the shock loads of logging operations. Shay replaced them with forged steel gears, machined to precise tolerances and heat-treated for maximum strength. The cost increase was substantial, $67 per gear set instead of $12, but the improved durability was essential. The drive shaft redesign was even more radical. Instead of one shaft with a 90-degree bend, Shay created a telescoping shaft system that could absorb length changes and angular variations. Each truck would have its own drive connection, allowing the locomotive to flex and twist while maintaining power to all wheels. The breakthrough that would define the Shay locomotive's success came when Shay realized he was solving the wrong problem. He had been trying to make gearing strong enough to survive railroad loads when he should have been designing a locomotive that prevented those destructive loads from occurring in the first place. The key insight involved power distribution timing. Conventional locomotives delivered power to drive wheels through rigid connecting rods that transmitted full cylinder pressure directly to the wheels in sharp, concentrated bursts. This created hammer blows that damaged track and caused wheels to slip on grades. Shay's vertical cylinders could deliver the same total power but spread across all wheels simultaneously through gearing. After months of testing, Shay determined that 3 vertical cylinders positioned along the right side of the boiler provided optimal power characteristics. The cylinders were staggered at 120-degree intervals, ensuring that at least one cylinder was always delivering peak pressure. This created smooth, continuous power delivery instead of the pulsing hammer effect of conventional locomotives. But the revolutionary element was the power transmission system. Instead of trying to drive all wheels from a single central drive shaft, Shay created a telescoping line shaft that ran beneath the locomotive, connecting to bevel gears mounted directly on each truck's axles. Each truck's gears distributed power to all wheels on that truck, meaning that a 2-truck locomotive powered 8 wheels simultaneously instead of the 2 or 4 drive wheels of conventional locomotives. The engineering mathematics were elegant and devastating to conventional railroad wisdom. A standard 20-ton locomotive transmitted approximately 12,000 pounds of drawbar pull through 4 drive wheels, creating pressure of 3,000 pounds per wheel. Shay's design distributed the same drawbar pull across 8 wheels, 1,500 pounds per wheel. This reduced ground pressure by exactly half, allowing operation on tracks that couldn't support conventional locomotives. More importantly, the geared drive system maintained constant mechanical advantage regardless of wheel diameter. Conventional locomotives lost efficiency as their large drive wheels wore down, changing their effective gear ratio. Shay's system maintained consistent 32-inch wheels that could be replaced individually without affecting the locomotive's performance characteristics. The gear ratio itself became Shay's masterstroke. After extensive testing on various grades, he determined that a 3-to-1 reduction between cylinder stroke and wheel rotation provided the optimal balance between speed and pulling power. This meant his locomotive would never exceed 15 miles per hour even on level track, laughably slow by railroad standards. But on a 4% grade, where conventional locomotives couldn't move at all, his locomotive could maintain 2-3 miles per hour while pulling loads that would stall engines twice its size. The 3-truck design that would become Shay's signature configuration emerged from pure mechanical necessity. Each truck pivoted independently on a vertical kingpin, allowing the locomotive to navigate curves as sharp as 40 degrees, curves where conventional locomotives would derail immediately. The articulated truck system also allowed the locomotive to twist and flex with track irregularities while maintaining power to all wheels. Testing the redesigned prototype required systematic comparison with conventional logging methods. Shay established a test grade on his property with a measured 13% slope, uneven temporary track, and a 35-degree curve, conditions that duplicated typical logging operations. The challenge would be moving 40 tons of logs up this grade, a load that represented one day's cutting by a typical logging crew. The test that would validate Shay's design began at dawn on September 17, 1880. On one side of the mountain, a team of 24 oxen prepared to haul 12 tons of logs up the test grade using conventional skid road methods. On the other side, Shay's rebuilt locomotive sat coupled to 40 tons of logs, more than 3 times the load that the ox teams would attempt. The ox team made their first attempt at 6:30 a.m., when the animals were fresh and the morning temperature was cool. The teamsters positioned their oxen in 4 6-animal strings, attached chains to the log bundle, and began the slow climb. The mathematics of animal power were unforgiving. 24 oxen could generate approximately 7,200 pounds of sustained pull, barely adequate for moving 12 tons up a 13% grade with friction losses on the rough skid road. The first attempt failed after 340 feet when 3 oxen lost their footing on a muddy section of the grade. The entire team had to be backed down and repositioned. The second attempt reached 520 feet before the animals simply stopped, exhausted from the sustained effort. By 11 a.m., after 4 attempts, the ox team had moved their 12-ton load approximately 800 feet up the mountain at a total cost of $8.40 in teamster wages and oxen rental. Shay's locomotive began its demonstration at 11:15 a.m. The vertical cylinders started their rhythmic pulse at 127 strokes per minute, driving the gear train that connected to all 8 wheels. The locomotive moved forward smoothly, its wheels turning at exactly 39 revolutions per minute under the heavy load. The 40-ton log train began moving up the grade at 211 miles per hour, slow by any railroad standard, but astonishingly fast compared to ox team speeds. The real test came at the steep section where the ox teams had struggled. Shay's locomotive passed through without any change in speed or cylinder pressure. The geared drive system distributed load evenly across all wheels, maintaining traction where conventional locomotives would have spun helplessly. At the 35-degree curve that would have derailed any standard locomotive, Shay's articulated truck system flexed and pivoted, maintaining power to all wheels while negotiating the sharp turn. The locomotive reached the top of the test grade in 23 minutes, having moved 40 tons of logs up a 13% grade with a sharp curve, conditions that conventional logging methods couldn't handle at any speed. The mathematics were irrefutable. Shay's machine had moved 3.3 times more weight than ox teams in less than half the time, using 1 operator instead of 4 teamsters. But the real validation came from the operating costs. Shay calculated that his locomotive could move logs at a cost of about cents per ton mile, compared to 31 cents per ton mile for ox teams. The difference wasn't marginal, it was transformative. Timber stands that were economically inaccessible using animal power suddenly became profitable using geared locomotives. Word of Shay's successful demonstration spread through Michigan's lumber industry faster than forest fire. Within 3 weeks, 5 logging company owners had visited Herring to witness the locomotive's performance. Each one arrived skeptical and left convinced that geared power represented the future of mountain logging. The project that would prove the Shay locomotive could transform an entire industry arrived in the form of a desperate telegram in February 1882. Have 80 million board feet on grades no team can reach. Stop needs solution within 60 days or lose timber rights. Stop. Can your locomotive work? Stop John Cass. The Cass Lumber Company's problem represented everything that was wrong with conventional logging methods. They had purchased timber rights to 14,000 acres of virgin West Virginia forest, but 73% of that timber stood on mountainsides, with grades exceeding 12%. Ox teams couldn't reach it. Conventional locomotives couldn't climb to it. The company faced financial ruin unless they could develop a way to harvest timber that every expert said was inaccessible. Shay personally supervised the installation of his locomotive at the Cass operation in March 1882. The challenge was more severe than anything he had tested in Michigan. The main logging grade climbed from the sawmill at 1,920 feet elevation to cutting areas at 3,400 feet, a vertical rise of 1,480 feet, over 87 miles of track. Sections of the line included grades reaching 14.2%, curves as sharp as 48 degrees, and a temporary track laid directly on the forest floor with minimal preparation. The results exceeded even Shay's projections. His locomotive could pull 47 tons of logs down from the high cutting areas, making the round trip in 4.5 hours, including loading time. The same timber would have required 14 ox teams working 2.5 days to move, at costs that made the operation marginally profitable at best. More importantly, the Shay locomotive could reach timber stands that were simply impossible to access using conventional methods. Cass's logging superintendent calculated that the locomotive made 27 million board feet of previously inaccessible timber suddenly profitable to harvest. At $12.50 per thousand board feet, that represented $337,500 in timber value that would have remained standing using any other transportation method. The mechanical reliability proved equally impressive. Operating 6 days per week through the brutal summer of 1882, the locomotive accumulated 1,247 hours of service without major mechanical failure. The geared drive system absorbed shocks and stresses that would have destroyed conventional locomotive machinery. The articulated truck system navigated curves and track irregularities that would have derailed rigid-frame locomotives daily. Industry publications quickly recognized the significance of the Cass operation. Railway Age published a detailed technical analysis titled "Geared Locomotives Solve the Mountain Logging Problem," documenting how Shay's design had achieved what conventional railroad engineering had declared impossible. The article included systematic comparisons of operating costs, hauling capacity, and mechanical reliability that validated every claim Shay had made about his locomotive's capabilities. By December 1882, Shay had received orders for 17 additional locomotives from logging companies throughout the Appalachian region. The demonstration at Cass had eliminated professional skepticism and established geared locomotives as proven technology for mountain logging. Each installation generated additional orders as contractors witnessed performance that conventional locomotives couldn't match. The financial impact extended beyond Shay's manufacturing success. The logging industry's access to previously unreachable timber stands transformed regional economics. Small logging operations could compete with major companies by using Shay locomotives to reach premium timber on terrain that larger operations couldn't access profitably. Railroad logging replaced muscle power as the standard method for mountain operations throughout the eastern United States. By 1910, Shay locomotives had fundamentally transformed American logging operations. Lima Locomotive Works, which had purchased Shay's patent rights in 1884, had manufactured 2,761 Shay locomotives operating across every timber-producing region in North America. The design that railroad engineers had dismissed as mechanically unsound had become the standard power for mountain logging, mining operations, and any industrial application requiring maximum pulling power on minimal infrastructure. The engineering principles that Shay had discovered, power distribution across all wheels, geared drive systems for mechanical advantage, articulated truck designs for track flexibility, became standard practice for industrial locomotives. But no subsequent design ever matched the Shay's ability to move extreme loads on impossible terrain. Modern logging operations using diesel locomotives and improved chin track could move timber faster, but they couldn't operate on the steep grades and sharp curves that Shay locomotives handled routinely. The performance records established by Shay locomotives remained unmatched through the end of steam power. In 1923, a 3-truck Shay operating on Oregon's Coast Range pulled 89 tons of logs up a 13.4% grade, a feat that required a drawbar pull exceeding 47,000 pounds. Modern diesel locomotives with twice the weight and 3 times the horsepower cannot replicate this performance on similar grades because their wheel slip characteristics prevent them from utilizing their theoretical power advantage. The irony of the Shay locomotive's success was that it succeeded precisely because it violated every principle of efficient railroad design. It was slow, 15 miles per hour maximum on level track. It was mechanically complex, requiring skilled maintenance that conventional locomotives didn't need. It was expensive, costing $8,400 compared to $4,200 for comparable conventional locomotives. But for operations requiring maximum pulling power on minimum infrastructure, nothing else could match its capabilities. The legacy extended beyond logging operations to influence industrial railroad design permanently. Mine locomotives, plantation railways, and military operations all adopted variations of Shay's geared drive principles. The mechanical concepts he had developed to solve logging problems, distributed power, flexible drive systems, high mechanical advantage, became standard features of specialized locomotives worldwide. Professor Richard Whitman, who had studied industrial locomotive development for the American Society of Mechanical Engineers, summarized the Shay's significance in a 1948 technical paper. Ephraim Shay's locomotive succeeded not by matching conventional railroad performance, but by completely redefining what locomotive performance meant. He built a machine for conditions that railroad engineers had never seriously considered, and in doing so, created the most powerful locomotive design relative to its weight ever developed. The last Shay locomotives manufactured in 1945 were still operating in commercial service through the 1960s, working on grades and curves that modern locomotives couldn't attempt. Their longevity testified to the durability of Shay's original engineering principles: robust gearing, distributed loads, and mechanical systems designed to survive conditions that would destroy conventional machinery. Today, restored Shay locomotives still operate on heritage railroads, demonstrating the same abilities that astonished logging crews in the 1880s. They climb grades that derail modern tourist locomotives. They navigate curves that require modern trains to slow to walking speeds. And they proved that the tiny engine railroad experts dismissed as mechanically unsound was actually one of the strongest machines ever built. The concrete foundation of American industrial logging was built on Shay's insight that the greatest engineering challenges require machines designed for reality, not theory.